You get it? Okay. I will begin. Heavenly Father, we thank you for this day. And Lord, I thank you for these students. Pray just bless our time together, Lord. I pray. Amen. Okay, so first things first, let me state and prove theorem. If C is curve from P to Q and F is equal to the gradient of little f near C, then the line integral of f dot dr over the curve C is just equal to f of Q minus f of P. All right. So here I have in mind some curve. Here's my initial point P, the curve C, the point Q over there. Okay. So here's the proof. I mean, there is an assumption here. We're assuming that C is parametrized by a smooth path, or at least a couple times, at least once differentiable, I suppose. Suppose we have R is parametrized by, say, T naught to T1. That maps to C, which is assumed to be some subset of Rn. So here is a parameterization of C. Okay. Now, the central point here is that, and we're assuming, of course, again, that f is the gradient of some function f, right? Okay. So what happens when we take the time derivative of f composed with r of t? Well, we have a chain rule, right? And the chain rule here says that that's the gradient of f evaluated at the inside function, which here is r of t, dotted with dr dt, right? So this is one of our many chain rules. Okay? So this is what, you know, but of course, in the case that f is equal to the gradient of f, and here see what we have, this is actually equal to what? F of r of t, right? Right, because we're assuming that the force field is conservative, right? Remember, our definition of conservative force field is that it is equal to the gradient of some potential function. Here, the potential function is f. All right. Okay, anyway, so thus, if we look at the integral, the line integral along C of f dot dr, what do we have? We have the integral by definition, t naught to t1 of f of r of t dotted with dr dt by, definition of line integral that we talked about yesterday. But by the soon-to-be boxed in red equation, by this right here, right, we can rewrite this as the integral from t naught to t1 of the total derivative of the composite of little f with the parameterization r of t with the path. Right? But what's the integral of a derivative? I mean, remember the net change theorem from Calculus 1, whatever you called it? So if we integrate the derivative, then we have f of r of t1 minus f of r of t naught, right, by Calculus 1. And then what is r of t1 and what is r of t naught? I mean, by assumption, q is r of t1, right? by assumption, P is R of T naught. That's part of what I mean when I say parameterization of C. Right. Admittedly, I'm thinking of C as an oriented curve. It has starting point P and ending point Q. If we reverse the curve, it would change the answer, actually. But anyway, so what we got? We've got f of Q minus f of P, and there you go. This theorem has a name. This is the fundamental theorem of calculus for line integrals. FTC for line integrals. So what do you prefer? Yeah. Attendance.
Sorry, I really probably let you down there.
It's okay. I'm going to go on. So FTC for line integrals and Josiah. Let's see here. Another J name. What can I expect? Let's see here. So in Calculus 1, which do you prefer? Using the fundamental theorem of calculus, part 2, to calculate the antiderivative, to calculate an integral, or do you prefer calculating directly from the Riemann sum? FTC part 2. Now, if you're going to calculate a line integral, do you prefer using fundamental theorem of calculus for line integrals, or do you prefer working from the definition? FTC for line integrals. However, strings are attached. For FTC part 2 in Calculus 1, what condition is needed for there to be an antiderivative of the integrand? What's that? Continuity will suffice. We can even be greedier. We can do piecewise continuous. Even if the function can be pretty messed up, and integration will still make sense. Now here, though, the assumption that a potential function exists for a given vector field, that's a huge assumption, and it's just not true for all vector fields. So unfortunately, this shortcut only works for a special subclass of vector fields called conservative vector fields. All right? And so let me, again, state the definition of conservative vector field so that you know it. Definition, F is a conservative vector field on U, which is some subset of Rn, if there exists little f from U to the reals such that f is equal to the gradient of f on U. The assumption of domain is important. You can't talk about really whether a vector field is conservative or not without stating, well, without an understanding of what the domain is we're talking about. It matters. Some vector fields, you could have a formula for a vector field, and that vector field would be conservative for one choice of domain, but it would be non-conservative for another. We're going to see that. So the stipulation of the domain of the vector field actually matters. Oftentimes, we'll just use the greedy domain. What's the greedy domain for a vector field? Here. Usually, I just set U equal to the domain of the vector field as understood by mathematical greed. For example, if you had f of xy equal to, 1 over the square root of x squared plus y squared minus y comma x, for example, this vector field. What's the domain? What would be greater than 0? X times y. I can plug in x equals to 1, y equals to minus 1. That's fine. Cannot equal 0? Yes, indeed. The domain of f should be the punctured plane. R2 with the origin removed, aka the punctured plane. It's punctured because we've just poked a hole out of the middle of it. That's it. But yeah, anything else makes sense because the square root of x squared plus y squared, that's just the distance from the origin, right? So you can divide by the distance from the origin as long as you're not distant 0 from the origin, namely at the origin. But otherwise, it makes sense. What is this? Do you guys recognize this vector field? What if I rewrote this in polar coordinates? This is actually minus y over r, x over r, right? AKA sine theta, well, minus sine theta, right? Cosine theta. We gave a name to this thing before. Yeah, it's theta hat. It's perpendicular to r hat. What's r hat? Cosine sine, right? So these do dot product to 0. They're perpendicular, 90 degrees apart. And in fact, theta hat points in the direction of increasing theta. So what happens here? What happens here if you integrate f along a circle? So let's let CR be the counterclockwise oriented circle of radius r, centered at the origin, all right? There's another way of thinking about calculations which I haven't shared with you guys yet, and since it just kind of organically came up here now at the moment, I'm going to share it with you. We can also think about calculating line integrals geometrically. Sometimes you can just understand intuitively what dr vector hat should be, what it should be, right? So if we look at an infinitesimal line element here, right? If I go here, and I think about, just going a little bit, this would be like dr. So you should be able to see that that should just be really ds times theta hat, right? It's an infinitesimal arc length along the curve, and it's in the theta hat direction. That's the direction of the circle. So with this in mind, there's an intuitive way of doing these kinds of calculations. Sometimes you'll see this in physics or engineering. So for my f here, f is actually just theta hat, and I'm dotting with, well, theta hat ds. So theta hat dot theta hat's 1. And so this line integral is what? So what's the integral of ds over the circle?
R, right?
Yeah, it should be the circumference of the circle, right? So 2 pi r, yeah. So, given that, can this vector field be conservative? The way I just did this calculation is really weird, guys, compared to what I was doing last class, right? Did I parameterize the circle? No. I'm just working off raw geometric intuition to set up this integral. Suppose there was a potential function, right? And suppose this was equal to the integral of the gradient of f dot dr for some f. What would happen? P is equal to q, right? Take the same Pick a point on the circle, let it be the starting point and the ending point for the curve, right? Fundamental theorem of calculus for line integrals would then say that this is equal to f of q minus f of q, which would be 0, right? Is 0 equal to 2 pi r? It is not, right? So apparently this theta hat vector field is an example of a vector field which is not conservative. So this is one of the ways we can detect a vector field being not conservative. If we integrate a vector field around a loop and the integral is non-zero, it can't be conservative on a region which includes that loop. Okay, so we actually have, actually before I get to that, I should, a couple other sort of minor notational comments. Actually, one of them is notational, the other one is a little bit more conceptual. So the notational one is this. We can also define integral along C of p dx and the integral along C of q dy and the integral along C of r dz. And it's kind of important for me to do this because the way this is done is that's the integral of basically p dx dt dt over the, over the parameterization domain, integral from t naught to t1 of q dy dt dt, the integral from t naught to t1 of r dz dt dt. Where what I mean in more detail, guys, I just don't want to write on every one, but I'm fessing up, okay? This is the actual, this is r of x of t, y of t, z of t, dz dt. dt. In other words, or maybe, tell you what, forget that. I can do better. We're usually using our vector of t for the path parameterizing the curve. Here, r has got x, y, and z as its component functions. So these are also known as line integrals, but I don't know. Or these are integrals of differential forms, people will say. In and of themselves, the integral of p dx, integral of q dy, integral of r dz, these are not really that interesting. But when you put them together, what happens when you put them all together? What is the integral of p dx plus q dy plus r dz equal to? Well, if you look at it, it's the integral from t0 to t1 of p dx dt, right? Plus q dy dt plus r dz dt, which is what? Not the divergence. Well, the dot product is what you want to say. Right, dot product. So put some words in your mouth there, if you don't mind. PQR dot dx dt, dy dt, dz dt, like this. So in fact, this integral of f of r of t dot dr dt is equivalent to calculating the integral of p dx, the integral of q dy, the integral of r dz, and adding them together. All right? It's the same calculation, actually. See, because this thing I wrote, this last thing I wrote is just directly the definition of f dot dr. Okay? So, I mean, one way you could look at this, heuristically, dr is really dx, dy, dz. You could think of it that way. And the definition is just a scheme to calculate it. we have to choose a parameterization of the curve to actually do the calculation, usually. But there exist situations where you have some sort of pre-existing geometric notion of what dr should be, and then you can just do the integral without even stating a parameterization. You can just do it by raw geometric reasoning alone, like that. Okay, so let's see here. What else might we try to connect this to? So let's see. Integral of f dot dr over the curve is also the integral from t, so t0 to t1 of f of r of t dotted with dr dt, right? That's the definition. What is dr dt, guys? We could dr dt is the velocity, right? So we could rewrite that as what? We could rewrite that as the speed times the unit tangent. So this could be rewritten as f, I'll drop the dependence on the path there, f dot t, right, times ds dt, dt. And in fact, if you go back and look at how we defined the integral with respect to arc length, this is an integral with respect to arc length. It's the integral with respect to arc length over the curve of the tangential component along the curve of the force field over the arc length. So that's an important conceptual way of looking at that actually reveals, that goes back to our basic definition. And some people would start with this as the definition of the line integral. It says that you do the integral with respect to arc length of the tangential component of the vector field over the curve. That's what the line integral is. It's adding up the parts of the vector which line up with the curve going around the curve. That's what the line integral calculates. If you had a vector field which was everywhere perpendicular to your curve, then f dot t would always be 0, and your line integral would be 0. So this is conceptually a very important formula, this right here. Yet another way to look at the line integral. Okay? So the pdx plus qdy plus rdz thing is just a calculational nicety. Let me show you what I mean for a specific example. Yeah, over here. By the way, I'm always assuming that the path has parameterization r vector from t0 to t1 today, because otherwise I'd write it like 10 times. Okay? I did that over there. I didn't tell you what t0 and t1. I'm still assuming that it's a parameterization for the curve we're talking about. So this is the other way of, engineers are very fond of this method of calculation. So I don't know, let's say we had, let's see here, I don't know, circle like that. So here I'm looking at intersection of x squared plus y squared equals to 16 and z equals to 3. So in other words, it's the circle of radius 4 centered around the z-axis in the z equals 3 plane. Okay? And let's suppose that it's oriented in the usual right-handed sense. And then I want to calculate f equal to, let's see here, x plus y, z, and z squared. Oh, I'm going to regret that. 3. No, 7. No. Give me a number. 5. I'll take the 5. Okay, so I want to calculate, given all this setup, calculate the integral along the curve of f dot dr. So this is my curve, that circle in the z equals 3 plane. Okay, so here's the differential form calculation method. Here's what you do. You write down x is equal to 4 cosine t, y is 4 sine t, z Well, z is 3, all right? That's the parametric equations of my curve, okay? Then you take the differential of each. I get dx is minus 4 sine t dt. I get dy is 4 cosine t dt. I get dz is 0. 3, it's not changing. Okay? Then, what you do, integral of f dot dr is equal to the integral, and you don't even need to write this down really, I'm just writing it down to emphasize what I'm doing, guys. But it's p dx plus q dy plus r dz, that's the line integral. So my p here is this guy. This is my q, this is my r. So what's p dx? So you might even write one more step. This is x plus y dx plus z dy plus 5 dz. Now, at some point, it all boils back down to the parametric calculation. I mean, it's going to eventually get back to that. There's something I forgot to say. 0 less than or equal to t less than or equal to what? Yeah, 2 pi. We're going full circle. If I said that if you went around the circle 2 times, we have to go 0 to 4 pi, right? There could obviously be applications where you're interested in traversing the loop 30 times or something, right? I don't know. You're calculating work done on a CD player. Maybe it's thousands of times or something. I don't know, whatever. So x plus y is what? So you got 4 cosine t plus 4 sine t. Good grief. 4 cosine t. I've invented an extra plus. So 4 times cosine t plus 4 times sine t. What's my dx? Well, my dx is minus 4 sine t dt. And I have, again, Ha. We'll see who wins today. All right. Plus, now dz is 0. dy is what? Well, z is what? 3? So we got 3. And then what's my dy? 4 cosine t, right? I really should bring some tape. There we go. Stay? Stay? Okay. So, yeah, I got to get bigger markers. It's not doing it. Anyway, so that's what's above. And how does it work out? Looks like we've got, what, minus 16 sine squared t, minus 16 sine t cosine t, and then that's what, plus 12 cosine t? Is that right? The last two terms integrate to 0, because that's actually 8 times the sine of 2t, and cosine t is integrated over a full period. The sine of 2t is integrated over like a couple periods. Anyway, the last two integrals vanish. And the first one, well, sine squared integrated from 0 to 2 pi gives me pi. So that's minus 16 pi. So there you go. Anyway, this is the so-called, I don't know what's a good term for it, but this is sort of, you could say differential form calculation. I don't like that exactly. It's the method of differentials as it relates to the line integral anyway. you notice that in this whole way of thinking, did I ever write down what's missing is a discussion of this, right? See, this is missing. We never actually write the path directly. We just write the parametric equations. So that's the different way of thinking. Yeah. Same math. All right. I must move along. Actually, yeah, we're fine. We're fine. So let's see here. Couple things. First of all, why is it called a conservative vector field? Right? The reason for that is tied to physics. And we have pretty much all of the tools we need to understand that now. So let's do that. So suppose the given force field is the net force. Then what's that mean? That means we have F is equal to ma, right? Newton's second law. But A is also dv dt. Okay, A is the derivative of the velocity. The acceleration is the derivative of the velocity. Now, in physics, we use U for potential energy. And if F is conservative, minus the gradient of the potential energy function makes F conservative force field. I don't put that pesky minus in our definition of potential function, right? So in here, the potential function, the little f that I've talked about, there's no minus. We just assume that the vector field f is the gradient of little f, right? But physicists, they put a minus there. Why do they do that? Well, let's see why. So suppose the net force is f, and f is also a conservative force field. Let's look at the fundamental, fundamental theorem of line integrals. Let's calculate the work done along a curve, right? What's the integral of f dot dr? So again, this is the work done, right, by f. Along C. That was our motivation for making the line integral what it was. But now what else is this? This is actually the integral of, well, if it's the net force, this is what? This is m dv dt, right? Dot dr, right? Okay, but let's break it down a little bit further. This is the integral from, say, t0 to t1 of m dv dt dot v dt. Right? That's what the definition says. It says you take the force, you dot with the velocity, you integrate over the time. That's the line integral. That's what I did. But then there's something cool that happens here. This is actually the integral from t0 to t1 of 1/2 m, well, excuse me, the time derivative, total derivative of m over 2 v dot v. Now you say, what are you talking about? Well, if you don't believe me, and you shouldn't believe me, how do you check such a step? Just do this differentiation. What happens when we take the derivative of v dot v? We get dv dt dot v plus v dot dv dt, right? In other words, you get 2 v dot a. So, that's why this is equal to this. Because if you have d dt of m over 2, v dot v, you get m over 2 times 2 v dot a, which is also equal to f dot v in our current lingo, which is what I had here. I'm sorry, I'm not making it very, you can work it out. It's just a short calculation that that's the total derivative of 1/2 mv squared. V dot v is v squared, right? It's the speed squared. Well, what is that? Again, total change theorem here. Kind of the hero of today, I think. This is nothing more than 1/2 mv squared, evaluated at t equals to t1 minus 1/2 mv squared evaluated at t equals to t naught. Or you could say this is kinetic energy 1, or kinetic energy final minus kinetic energy initial, right? If you look at what I've just done, did I assume that the force was conservative in the calculation I just made? No, all I've used is that F is equal to ma so far. So the work energy theorem is something that's generally true for the net force. The work done by the net force is the change in kinetic energy for the mass in question. This is true for conservative or non-conservative forces. But something truly magical happens if F is a conservative force, because then we have that the integral over c is minus the gradient of u dot dr. Right? This assumes conservative. Right? And then we can use our fundamental theorem of calculus for line integrals. And this is what? Minus u final minus u initial. Right? But these two things are equal. And so what that gives us, of course, is that the kinetic energy final plus the potential energy final is equal to the kinetic energy initial plus the potential energy initial, right? Which is to say that the mechanical energy is conserved. And so that's why it's a conservative vector field, because it results in conservation of the net mechanical energy for the system in question. Make sense? I mean, I think that you might think that my definition of conservative, that it's the gradient of something, is a little bit weird, right? But it's not weird because of this. And pragmatically speaking, this is a much nicer definition to work with, because it's something very tangible that we can put our paws on as far as the calculus goes, all right? So let me, since my time is, well, I don't know. All right, so there's a theorem of equivalence that we need to start chipping away at. It's going to take me about probably a half-hour class to prove the thing. But this is important. I mean, this is like the central theorem of this part of the course. And it really, again, it relates to conservative vector fields and how do we understand them, how do we characterize them. There are four nice equivalent conditions. And I think rather than I'm the worst. I can't make a decision for save my life. So the following are equivalent. The following are equivalent for a vector field F. All right. Numero uno, F is conservative. And this is going to be, this is my proposition 7.45, if you're keeping track. All right, so number one, F is on U subset of Rn. And it's an open subset, which means it doesn't have, we talked about open versus closed. Remember that? It's that kind of open subset. So F is conservative on U. What's that mean? Again, F is equal to the gradient of some function F. That's number one. Number two, f is path independent on u. Now, we started talking about that yesterday, right? 2. And I'll write it down more technically. Integral of c1 of f dot dr is equal to the integral over c2 of f dot dr. And here's a picture to explain what's going on. Here's your c1, here's your c2, here's your universe of discussion u. So for any two paths with the same terminal starting and ending points in u, we get that the line integral of f along c1 is equal to the line integral of f along c2. All of this is succinctly summarized by saying f has path independence on u. The line integral doesn't care about which path you take. 3, the integral around the loop of the vector field is 0 for all loops C in U. And then 4, given n equals 3 and U simply connected. Simply connected, what on earth does that mean? Well, we'll have to talk about that. But I'll tell you this, the punctured plane is not simply connected. The curl of f equal to 0 on U. So we already, what is it? That means it's an integral around a loop. Yeah. Yeah, so like sometimes people will adorn that with like an even little arrow to indicate whether it's a clockwise or counterclockwise oriented integral. I still need to have the talk with you guys about orientation in integrals. We haven't had that talk yet. We should have that talk sometime. We're due for that talk about an hour ago. But, oh well. Yeah. So these are equivalent conditions. In other words, if I have any one of these, I can get the other. All right? Pragmatically speaking, these are kind of tough to check, right? Like, you got to do all possible line integrals from one point to another in the set. Like, that's a real pain to think about actually doing for a specific function, right? I mean, for a specific force field. So more often than not, what we actually calculate for a specific vector field is like the fourth one, because it's pretty easy to check the curl. That's a straight calculation, right? Curl is 0, your set's simply connected, whatever that means. It's conservative. Woohoo! Of course, if you can just find the f for which the gradient of the potential is the vector field, well, it's conservative. That's true. And that's actually not that hard for certain vector fields. We've already seen it. You guys guessed it on the fly, right? Sometimes it's essentially 3 integrals that are kind of interrelated, right? We should talk more about that. The most interesting part of proving this theorem, though, is showing that path independence implies the existence. So for me, the most interesting part of this theorem is proving that 2 implies 1. So proving 2 implies 1, the argument there is actually kind of subtle, quite beautiful, and actually is how we construct potential energy functions in physics. So anyway, if you don't like physics, I guess this is a bad part of the course for you. Sorry. But don't worry, we'll get back to multiple integration before too long. So if you're missing it, it's coming back. Right after this, we talk about Green's theorem, which is double integrals. And then after that, Stokes and divergence, that's all triple integral stuff again. So don't worry, they're coming back. I know you're missing it. So, all right, I should shut up because I think our time's up. Am I wrong? When do we wait a minute. Do I have until... I have 4 more minutes, don't I? You monsters. I could prove half of this in 4 minutes. Look. I've already got it up. I'm going to... Look. Come, you guys are killing me. You know, that would ruin the rest of my day to waste these 4 minutes. So to get 2 implies 3, how do you get 2 implies 3? So suppose I know that the integral along all paths, same starting and ending points, are equal. How would I get that the integral around all loops? So take any loop, right? Take any old loop, like this, in your set U. We're assuming 2 is true, right? So I'm trying to prove that 2 implies 3. So I assume 2 is true. Think about any loop in U, right? Pick 2 points on the loop. Say this one and this one, right? So you notice that this loop can be decomposed into what? C1 and C2. So C is the whole loop. Let's say that the loop was counterclockwise, all right? So C would be what? It would be C1 union with what? Minus C2, because it's in the opposite direction, right? So the loop is the union of C1 and minus C2. What do we know about? And then, so properties of the path, the line integral come into play here. Integral of C of f dot dr, which we could put, if we wanted to, we could put the little circle on it. The circle is nothing, I mean, that just emphasizes it's a loop. So it's optional. You don't have to put it there, but if you want to, you can. It's a loop. Yay. Okay. Now that's equal to the integral over C1 of f dot dr plus the integral over minus C2 of f dot dr, because that's one of the properties of line integrals. If you have 2 curves put together, then the integral over those 2 curves put together is the sum of the integrals over each curve respective. But then the line integral is oriented. See, this is why we should have had the talk. That means that when you have minus C2, that minus pulls out, and you can put it up here. So like integral over minus C2 is minus the integral of C2 of the force. But by path independence, these are what? These are equal. So that means that this is 0. And that's how you prove 2 implies 3. And if you look at it, it's pretty easy to reverse this argument, right? If you have 2 paths that go from the same initial to ending point, you can see there's a loop there, right? So you can basically the same arithmetic shows you that 3 implies 2. So 2 if and only if 3 is just really a topological observation. It just has to do with the, shape of the paths and their interconnectedness. Anyway, we'll talk more about the rest of it tomorrow. So, thanks, guys. I still ended a minute early. Woo!